online streaming.
Okay, just let me know when.
You can start anytime. It's just we'll just join as it comes in.
Okay, so another way of getting around this problem is with an antenna tuner. So what does an antenna tuner do? Well, it kind of matches the impedance of your antenna to your transmitter. That's what it does. It used to be called a matchbox, and the AARL insisted that it be called a matchbox because that's what it is. But amateurs call it antenna tuner. And it really doesn't tune the antenna. If you were tuning the antenna, you would be cutting pieces of wire or adding pieces of wire to get your resonant frequency. So it's really not doing that. It's just putting inductance and capacitance in so that you get a good match. But the thing to keep in mind with an antenna tuner, it's fooling around with this stuff. So it's not a resonant antenna at this point, and there's going to be some loss of radiated power. So it's not as good as if you had a resonant antenna. But you know, the reality is you can't have a resonant antenna on all frequencies. So this is a way of getting around that problem. So in certain areas, you're going to have a reduction of power. But on HF, it really doesn't make a lot of difference. The difference between 50 watts and 100 watts on HF is almost nothing. You know, in terms of, on your meter is going to read S units, they call it S units. It's going to make almost no difference in S units. So it's a way of getting around the problem of having an antenna that will work on all frequencies. Yeah, so your radiating power is reduced. Impedance. Remember that impedance is a mixture of resistance and reactance. Resistance because it's a piece of metal. Reactance because you're putting alternating current on it. Okay, so you're going to have impedance on your antenna. So here's a picture. I'm going to give you a video of this as well. For the half-wave dipole antenna, here's a picture. You have voltage maximum at the ends and current maximum in the middle. Okay? So that's something that you need to remember. And this will determine how you feed the antenna. Also, it's telling you that as your voltage is high at the ends, it's telling you that that's where you're going to get the maximum damage from the end of the half-wave dipole antenna. If you touch the end while this RF is going through there, you're going to get a nasty burn. And the joke about that in amateur radio is megahertz. Megahertz. Okay, here we go for the video. This is going to work. Should go. Didn't go. There we go. Now there it is there. I'm going to blow it up. Whoa, too much. So this is a receiving antenna, and here you see the wave coming in on the receiving. There's the antenna there, and you see the wave coming in, here's the antenna here, and you see the wave coming in. You see the voltage peaks, and you see the current going through the antenna. Isn't that a neat diagram? Very, very neat. That's from Wikipedia, by the way. Okay, here's another one, basically same thing. And here's it's a better picture. It shows you the current in blue and the voltage in red, and how they're changing. That's basically what your antenna is doing. It's doing that both on receive and transmit. So the electromagnetic wave is inducing a voltage and a current. When you're receiving, it's inducing a voltage and a current in your antenna. It's very weak, but it's still there. Okay, so in the center, we said we have high current, low voltage. This means we have low impedance at the center of the antenna, so you can match it with a low impedance line such as coax. Normally, it's about 73, 75 ohms, but 50 ohm coax cable will work fine. Now, if you want to feed it at the end, we call it a half-wave Sept. You've got low current, high voltage, then your impedance is going to be high, and you need to use twin lead there. 300 ohm, 600 ohm cable, if you're going to feed it there. Okay? Which is something we already went through here. So if you have that Sept, you're feeding it at the high voltage end with 300 ohm line, then you're going to need, your transmitter is 50 ohm, then you're going to have to use a balun. And a balun is a matching transformer. It's going to take the 300 ohm and it's going to convert it to 50 ohm so that you'll get a match, okay? That's the purpose of a balun. Actually, balun means balance to unbalanced. Feed line is balanced. Coax is unbalanced. So balun means balanced to unbalanced. Okay, types of antennas. We finished the theoretical part, and these are just types of antennas. You have the dipole, it's also called the Hertz, the Marconi, or the doublet. The inverted V, the trap dipole, the folded dipole, the long wire, the vertical, the Yagi or the beam, and the dummy load. Whoa, we're going to talk about dummies. So, the thing to keep in mind is all of these antennas, even the Yagi, is based upon the dipole. See? That's essentially a dipole. It's a Yagi antenna, but it's using a dipole. All antennas essentially use dipoles. Okay. Here's a question about the dipole, and the question the ends of the suspended wire at the ends of the suspended wire insulators are used. These act to what do the insulators do? Yes, B. Now most people think the insulators are used to support the antenna. Support is part of it, right? But really they're limiting the electrical length. So if you have the insulator and it's got a hole in here, this end is going to the rope, this end is where the wire is. Okay, when you're tuning your antenna, if you're making your antenna shorter, then what you're doing is you're looping it through, you're pulling it back, you're twisting it around, right? Even though this is twisted around, it's the same electrical, it's the electrical length that matters, not the twisted around part. So then you test it to see, transmit through it, see what the SWR is, and then you might loosen it off, slack it off. It's a little too high, you want to make it a little lower, slack it off, get that little piece longer, and test it again. So it's the electrical length that the insulator is controlling. 40 meter antenna, half wave, 7 8. This is something you'd have to memorize. Can be used on another band without tuning. Does anybody know the answer to this? What band can use a 40 meter antenna other than 40 meters? Now, all the bands are related harmonically. Would it be 20 meters? You would think so, but it's actually 15 meters. That's what I would have said too, George. Yeah, it's actually 15 meters that it works on. Now, we get some expert to tell us why. It works on 15 years. But if you have a G5 or a V or another Sept antenna, this isn't going to work. You have to have a 40 meter dipole that to make it work. Okay, so that's one question. Now, if you can't fit the dipole in your backyard, there's a number of things you can do. You can bend the legs of them around. Now this is going to change the radiation pattern, okay? It's going to change it, but it's going to work. You bend the legs around somehow because some of this wire is getting pretty long. Or you use a loading coil. And a loading coil is just like more antenna, but it's just wrapped on some type of form. And this is going to increase the length of the antenna using the loading coil without actually increasing the physical length. You're increasing the length of the antenna without actually increasing the physical length. So this is a homemade loading coil. You can do that yourself. It takes a lot of experimentation though. So it's better to get some notes on this to get how many turns you need for which antenna. Okay? But that's the question that you're going to get from the question bank. The inverted V, this is essentially a dipole that slopes down in the form of a V. That's all that it is. And here it is here. 40 meters, inverted V. Huh. Boy, we drive 10. Okay. The angle at the apex here is 90 to 120 degrees. You know, when you get to your property, you could just do with it what you got in the property. So it might be more than 120 degrees. It's not really going to make a difference. But the ends have to be high enough so that people don't contact. Remember, this end here is high current or high voltage. High voltage. Somebody touches that, megahertz. Okay? Now, the way it works, remember, we have the chart here. The higher the band, the greater the energy. So this configuration may be okay on 80 meters. But when you get 10 meters, get this in 10 meters, and that's just a couple of foot off the ground and close to people, then it's going to start to become big. Too much radiation. Somebody touches it or a pet can get to it. No, it's a problem. But you'll be getting that later on in terms of safety. The impedance of this antenna is 50 ohms, and as we said here, it's dangerous on 10 meters. Trapped dipoles. This is another way of getting around fitting it in the space. You know, space is always limited. It's going to give you multiple band operation. It introduces parallel tuned circuits or traps into the radiator. Here is a layout of a 48 meter trapped dipole. Okay, and there's a choke. Okay, so there's a difference between a choke and a balun. There's a choke on here. A balun is like a transformer. It's matching impedances. It's going to take you from 300 ohms, usually, typically 300 ohms to 50 ohms. What is that? 4 to 1? 4 to 1. 300 divided by 50. 6 to 1? There you go. Okay. A choke is a different kind of fish. What a choke is a possibility when you're using coax that you could be radiating from the mesh, the ground side. Okay? Because the ground is on the ground, but the ground is not up on your antenna. You know? So there's a possibility that the sheath, the coax is going to radiate. And if it radiates, it's going to change the pattern, it's going to cause all kinds of trouble. So you put this choke in, and there's diagrams on how you do this. You put the choke in, and that stops the ground from radiating. And they call it a choke balun. I would call it just a choke, because it's not matching impedance. Anyway, the traps. How do the traps work? Well, it's a tuned parallel circuit. You have to remember the tuned parallel circuit is the highest impedance at its resonant frequency. So its impedance is high. That means it's acting like a brick wall. Okay, it's cutting the power off. That's what it's doing. It's stopping everything at its resonance frequency. So just to go back to the antenna, if this will work on 40 meters. If this is tuned to 40 meters, then when the power gets there, boom, it's cutting it off, stopping it. So this part of the antenna cannot be used because that is stopping it on both sides. But When you use this on 80 meters, it's like an open, it's like a piece of wire. The power is going straight through, so then you get to use the other length of the antenna, and it'll work on 80 meters. So it works on both bands that way. Yes.
Could you put two traps on each
You
side
can.
and make it into like a tug of war?
Yeah, you can. But it gets very complicated. You know, the distances get changed because of the traps. So you have to, you know, get somebody who's worked it all out with exactly how long it would be. But you could make a multi-band antenna this way. Now you will see on Yagi antennas, you will see the Yagi. Typically, when we buy Yagis, they're 20, 20, 15, 10 meters, and they have traps on them to make them work. Okay? Because a monobander, like, why put one up for just one band? That's a lot of money. So most of the times, your Yagi antenna is trapped. Okay. So there we go. And this is just what I said. If the resident frequency set at 20 meter band, the trap will prevent the use of the end portions of the antenna when the antenna is on 40 meters. The antenna is on 80 meters, the ends of the antenna won't be blocked. Here's a folded dipole. You don't have to know much about a folded dipole except that it's a full wave antenna. These are not folded dipoles. It's a full wave antenna folded back on itself, has impedance of 300 ohms. That's the kind of question you're going to ask in a question. Oh, it says the full wave, and my thing is showing a half wave. Okay.
So is it a half wave per side?
It's the side is half wave. Yes, it's full wave in total. Right. Yeah. Long wire antenna. We're just going through these briefly. It must be 3/4 of a wavelength on the lowest frequency. And the problem with it is, it's usually you usually feed it from the end. There it is there, and you're feeding it usually with twin lead. So how this works, I don't know. You bring the twin lead into your shack, and it's always a problem when you bring the twin lead into the shack because the RF is right there. There's no shield, and it's dangerous and it can cause all kinds of problems. But Tony, who was teaching them, that's what he has in his house is a Carolina Wyndham, and the twin lead is right into his house. Okay, and he says it doesn't cause him any problems. It's not something I would do. I would only bring coax into my house.
Bruce, come on. The twin lead is twisted
Yeah. Twin lead is twisted, yes.
to cancel out.
Yeah. To cancel out the radiation. There you go. You can twist the twin lead. Still don't trust it. And in your long wire, you can use a balun to bring it to 50 ohm coax. And you have to use an antenna too. The vertical is a half of a dipole mounted vertically. It's a quarter wave. One half of the antenna is missing, but the other half is provided by ground. By the ground. The impedance is 36 ohms. They'll ask you a question on the question bank. What's the impedance of a ground-mounted vertical? Well, you have to memorize it, unfortunately. This is omnidirectional. It's isotropic radiator. It's omnidirectional like a light bulb. It's useful for DX because it has the low angle of radiation. It's susceptible to noise, which is vertically polarized. Noise is vertically polarized, so it's going to pick up noise. But a lot of radio amateurs use it because of that low angle of radiation. Good for DX. It has to have some ground reference, and you get it two ways. You get a ground plane, or you get a system of radio. Now, you've probably seen those antennas. They're all over. You know, taxi cabs use them, and they got their antenna. And then you see all of this. They mounted it up, and you see that sort of thing mounted on the side of a house. So this is your ground plane. You have to have some reference so that these are going to bounce or whatever it's going to be going right there. Okay? If you don't do that, you mount it right on the ground, then you have to run radio wires in the ground to make the antenna work properly because it doesn't half the antenna is missing. If you use a quarter wave antenna on your car, right, then the car body is providing missing half of the antenna. Okay. Now, in the old days, my father was in the British Army, and he was interested. He made his own radio sets, superhets, they call them, superhets or diamond receivers, and he had an antenna. And he used to go out with a hose and water his antenna. Why do you think he was doing that? He'd water the antenna. He was in India while he was doing it. No, no, I didn't even think. No, it's the same thing. He was providing a better ground reference for the antenna. It works better with a better ground reference. That's why antennas, I believe, work better by lakes or on lakes, because it's providing a good ground reflection. Okay. Yeah, so we went through this. With vertical antenna, you bury the radio wires in the ground. Okay, the Yagi. You don't have to know the spacing of the Yagi and the percentage that each element is reduced, but you do have to know what they are. And you have the driven element in the center. This is the driven element, of course. And you have the a reflector element and a director element. And these two elements are called parasitic. And the reason that they are parasitic is because they get their power from the driven element, although they're not connected to it. And so they're getting their power, and they are then using that power to create a beam that's going to be directed this way. Okay, that's what this whole operation is doing. Now remember, as we said before, the gain is in this direction, but it becomes very directive. You need to rotate it to be able to pick up that signal. Now the advantage of this, it is a disadvantage, of course, that you have to move it around to get what you want to listen to. But the other advantage is this antenna is going to eliminate noise, because something interfering signal, let's say coming from this direction, you're not going to hear it. You're going to hear it front or back, but you're not going to hear it from the side. So if there's any noise, a QRM as we call it in radio, that's coming from this side, it's canceled out. It's only going to be operating that way, in the direction that it's pointing. Now I have a program at home. When I log onto a station, it tells me the distance to the station, and it also tells me the bearing. And the program is sophisticated enough that if I had set this up, it will actually turn the rotor of a beam to that bearing. So it'll say, Timbuktu, it's 4,000 miles away, and your bearing is 256 degrees, and the antenna would go and push this right on that location. Okay. So this type of electronics is all available in radio. Okay, so these you just have to memorize them. They're going to ask you questions about them. And we talked about parasitic. They're parasitic because they are not driven. With no power connected to them, they get the power from the driven element. It's highly directive and has considerable gain. You can get beams of 10 decibel beam. That's 10 decibels. That's really good. I showed you one of 18.5 decibels. And we went through most of this, that the beam has to be rotated. However, the cost is significant. You need a tower and a beam, and it becomes a significant cost. But if you got the money, that's the way to go. A dummy load is not for dummies. It's a device, it's made up of resistors, and it duplicates the function of antenna without radiating. It's used for testing a transmitter. Okay, nowadays, you could probably use a dummy load if you wanted to, but the way most transmitters are nowadays, is an antenna tuner inside of it. You push the antenna tuner button once, just click and release, and then it'll go click, 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 and in a less than a second, it puts in the capacitance and inductance that's needed, and you've got a one-to-one SWR. And when it does that, it puts out like maybe 2 watts of power. So you don't need to do anything. Really, you don't really need a dummy load. Now, if you've got a big, amplifier, then you may need to test your amplifier by using a dummy load. Most amateurs really nowadays really don't need a dummy load. Standing wave ratio. This is what we need to get to. It's a measurement which indicates the effectiveness of the power transfer between the transmitter and the transmission line and the antenna. SWR. And there are many great debates about SWR, standing wave ratio, or sometimes it's called VSWR, voltage standing wave ratio. Okay, at the resonant frequency that antenna is cut for, you're going to have a 1-to-1 SWR. And that means that it's the most effective match, and it's radiating the most effectively that it can. The 1-to-1, that's what you want. An antenna tuner will give you 1-to-1, right, in all kinds of places on the band. But remember, it's not a real 1-to-1. It's a simulated 1-to-1 that it's giving you by putting inductance and capacitance in. Okay, so the 1-to-1 gives you the maximum power transfer. An SWR of 2-to-1 is considered satisfactory amateur bands. However, anything higher means that energy is going back into your radio transmitter. It's going into the finals. So we want it all to go out of the antenna. We don't want any coming back. But if the SWR goes off, then the power is coming back to your antenna, into your transmitter, and it could cook your finals. It could overheat your radio transmitter, which is not a good thing. Okay, so here we have a cross needle SWR meter, and you probably won't have this on most transmitters. And there's 2 scales, you see, the forward and reflective power. The forward and the reflective power. Now, ideally what we want is we want all forward power and little or no reflective power. And as you can see from these scales, if this reflected power one doesn't move, if that one stays down there, then you'll always have a 1-to-1, no matter what this goes up to. See, what's the 500 scale, there's 500, 600, 700 watts, okay? This is going to go up, but where they cross is where your SWR is. Okay, 3, 5 to 1%. These are not acceptable. Okay, these are acceptable. So what it's actually doing is measuring the voltage going out and coming back. That's what it's actually doing.
So where the system, there's 2 needles on there.
Yeah, and they cross.
So where should they be? Both at 1 and the other one at 1?
Where we really like it is if this one doesn't move at all. But if you're putting out 100 watts on that band, on this scale, because you got a range here, 100 watts is where? Right there.
Okay.
So that goes, you're putting out 100 watts. That's good if that stays there. But if this one jumps up, then your SWR is up. So SWR is measuring the power that's going out versus the power that's coming back. And we want more power to go out than come back. We don't want power coming back, because if it comes back, it's going to cause us trouble. Okay? That's why we want an SWR of 1-to-1. If there's no reflected power, the SWR will be 1-to-1. As the reflected power increases due to the antenna being out of its bandwidth, then the SWR will increase. The reflected and forward power react on the transmission line to create what's called standing waves. You get standing waves on the transmission line. Could be a question on that in the question paper. Standing waves on the transmission line means that your SWR is high. You haven't got a match. Okay? And as I said, it's comparing forward and reflected power, that's what the meter is doing. It's measuring the match between the transmission and the antenna. It's not measuring the match between the transmitter and the transmission line. It's measuring the match between the transmitter and the antenna. That's what SWR is doing. Now, this is a nice little chart that I wrote up. The antenna tuner makes it appear as if there's a one-to-one match. However, the actual power is used. So here we have an example for you. Okay, here's a band. Here's the band here, and here's the frequency the antenna is cut for, 3.6 megahertz. Okay, it's resonant at 3.6 megahertz. Our antenna that we cut it. We cut it for that 80-meter antenna. We put it up. Okay, we're going to get 300 kilohertz bandwidth. So we get on this side, we get 3.45 megahertz. On this side, we get 3.750 megahertz. Bad right. Anyway, so there's our bandwidth. This is all our bandwidth. Okay, but we haven't got enough on this band. That's our bandwidth. And we're getting a 2-to-1. We're getting a 1-to-1 right there. But by the time we get to the ends, we're getting a 2-to-1. And 2-to-1 is acceptable in an amateur radio series. 2-to-1 is acceptable. If we go beyond this, then we're going to be getting 2.5, 3, and the farther we go out here in transmitting, the worse the SWR, the more power is coming back into the finals of our transmitter and blowing it up. The good news is that all modern transmitters have circuits in them that when the finals start to heat up, they cut the power down. Even these little guys will do that. Okay, so you don't have to worry about it that much. But you'll be wondering, why is this thing really not working that well? Why is this thing heating up? Well, yeah, because you haven't got a match anymore. Okay, so beyond your bandwidth, you're going to be using your antenna tube. Here, so here you use your antenna tuner. And it will simulate a 1-to-1. It'll simulate a 1-to-1 match. It's not really a 1-to-1, but it will simulate a 1-to-1. Really, that antenna is only cut for 3.6 megahertz. It will operate the whole band with the antenna tuner. Okay? Any questions about that? How that works? So you see, originally we started off thinking, gee, we're going to have to cut an antenna for every frequency. You know, to have a resonant antenna, we don't really need to do that. We've got the bandwidth that helps us out, and we've got the antenna tuner that helps us out, so that we can cut one antenna and use it for the whole band. And you know, nowadays, like my antenna tuner in my TS590, boy, I think it'll almost tune a 5-to-1. So that badly mismatched, and it'll tune it. I can tune the 30-meter band, which I couldn't tune before on the 570, and I can tune the 6-meter band. And it's not that the G5RB is not made for those frequencies. But the antenna tuners are so good now that they will match on those frequencies. The problem again is it's not going to be radiating all the power it should. Radiated power is going to be kept down, but it'll work. Okay, we're just getting close to it. Here is something that's not on the test, but this is the antenna that, not covered in the book, it should be. This is what most people are using in the amateur radio community. I know that Mike has one. I know that you don't have one? No, okay. I have one. I know a lot of people have them. Mark, VE3 FOG makes them. Yes.
One thing I was going to tell you, remember Sean?
Yes.
He bought Alan's old radio. He hooked it up to his G5RB. It wouldn't match on 10 meters.
Huh.
But add in 75 feet of coax, Works fine now. It'll tune it.
Ah, yes, okay.
You see what's going on now.
I was told that I needed, what does it say?
It says 50 or 75 ohm coax, but they're saying for certain radios, some radios will their tuners are fine, but if you, some of them are actually saying you actually require anywhere from 50 to 75 feet or longer of coax to actually for the tuner to make it work right to tune it.
I was told I needed 100 feet. Mine has got 100 feet of coax.
Yeah, roughly, yeah, 75 plus, yeah.
So you see the G5RB. Now, believe it or not, it's hard to believe. This antenna will work on the 80, 40, 20, 17, 12, 15, and 10 meter bands.
6 meter too.
Yours works on mine will work on 6 meters as well.
Yeah.
So it's a multi-band antenna. Now, how does the darn thing work? Well, you've got these two elements, and the one I have there's a whole bunch of different models of this, okay? And it's called a G5RB because G5RB was the call of the British amateur that invented it, okay? And this is a super duper antenna. This is the best thing you could get. You can make it yourself, or you could buy them commercially. Okay, these, in the one that I have, these are 51 feet each side. And this piece is twin lead, and it's 29 feet. So it's got to be 29 feet up in the air. What does it say? 25 to 50 feet. So it's got to be that high up in the air. With this twin lead, you've got to make sure that it doesn't come into contact with any metal. That's a no-no. So this has to be spaced off from your soffit and whatnot in the building to make sure there's no metal. Spaced off from the pole. You know, to use an insulator made out of PVC. You know, to just stand it off from the pole. Otherwise, it's going to be screwy. Then you need your balun to go from the 300 ohm to the 50 or 75 ohm. And with mine, I've got 100 feet of coax on it. And I think you need the 100 feet of coax, I was told, to make it work. And it will tune, you still need an antenna tuner, but it will tune every band. Just one antenna. Originally, I had mine in a inverted V formation. I recently flat topped it in the hope that I would get low angle radiation off of it. I've worked the world on this antenna. I've worked everywhere in the world, including China, Somalia, Korea, etc., on this dinky little antenna. Okay, so it works great. It's cheap. It's easy to put up, etc. If you're going to get on HF, I would recommend it.
Is there a special orientation for that as far as like north, south, east, and west that should be?
You pretty well have to put it where your property is.
So the north and south direction doesn't matter as long as it's horizontal?
Yeah.
It doesn't matter which way it is?
It's going to make a difference on the lobes, but you're stuck with whatever piece of property is. This is the explanation that I just gave you. Just one other point. The 5/8 radiator, they go through pages and pages of it. There it is right there. The only reason that in the mobiles and base stations they use the 5/8 radiator, I've said this before, as low angle radiation. That's why it's used. And that's the typical question on the question bank. What is the main reason that so many VHF base and mobile antennas in the amateur service are 5 wavelengths, are at 5 wavelengths? The angle of radiation is low. Where is that? Most of the energy is radiated at low angle. That's why that antenna is used. Any questions before you pack it in? I wanted to show you one other thing. We got seconds left here. This, if you're going to get an antenna, buy one of these. They're about $60. This connects to the ground, right? And it'll tell you which side is in and which side is out. Don't see it right now, but in any event, this goes to the antenna, this goes to your transmitter. If you have a lightning storm, if the lightning directly hits your antenna, it's fried and your equipment is fried, forget it. There's nothing you can do if it directly hits it. But that's not the problem in the amateur service. The problem is that you get a static discharge. It hits somewhere else, and you're getting a static discharge, and that will blow out your equipment. This device takes static discharges and brings them to ground. It saves your equipment. And this device works from, I don't know, 1 megahertz right up to, probably the 440 meter band. So very useful. It has a gas discharge tube inside. And if that tube blows out, you get a discharge and it blows out, you can buy a new one. So this is a very useful device for handling. That's it, folks.